Okay, this is questions on capacitance. Question 1. An insulated metal sphere carries a charge of 50 millicoulombs at a potential of 200 volts. What is its capacitance? Well, as we've seen, capacitance is defined as the amount of charge per unit volt that can be stored. So given the information here, we've got 50 millicoulombs, which we can write as 50 times 10 to the negative 3 coulombs divided by 200 volts, and so we get as an answer 2.5 times 10 to the negative 7 farad. Question 2. A capacitor of capacitance 4.7 millifarads is charged fully by connecting it to a 12 volt DC supply. Calculate the charge stored on the plates of the capacitor. So just rearranging the capacitance equation, making charge the subject, Q equals C times V, and then putting the values carefully. 4.7 times 10 to the negative 3 is our capacitance value, and multiplying that by 12. The voltage, we end up with 5.64 times 10 to the negative 2 coulombs. Question 3. A 12 millifarad capacitor is connected in series with a 6 millifarad capacitor. What is their combined capacitance? So to calculate that, we use the series capacitance formula, which is similar to the parallel resistance formula. We take 1 over 12 plus 1 over 6 and to the power of minus 1. Invert everything once we sum it. So that ends up being 4.0 millicoulombs. Okay, question 3, continued. That pair of capacitors is now connected across a 36 volt DC supply. What is the charge in each capacitor and what is the PD across each capacitor? Now, because they are in series, we have the same charge across the combination as we do for each capacitor individually, and therefore we can use this equation Q equals CV, and just being careful to use the 4 millicoulombs, so times 10 to the negative 3 multiplied by that 36 volts to give us the answer, and that should be 1.44 times 10 to the negative 1 coulombs. The PD across each capacitor next. Let's just choose the V across the 12 millifarad capacitor. We're just going to use Q upon C, but we have to use the charge we've just calculated, the total charge of course, for the Q value, and divide it by 12 millifarads in this case. So if you do that carefully, you should get 12 volts. That's nice, isn't it? 12 volts across a 12 millifarad capacitor. That leaves the remainder of the 36 volts for the other capacitor, the 6 millifarad capacitor, therefore has 36 volts. Take away that 12 or 24 volts. Now you could actually use that ratio again using 1.44 to the power of negative 1 and divide it by the 6 millifarad value. You get 24 again, same way, the same final answer. Number 4, find the charge and energy stored by a 1000 millifarad capacitor when it has a PD of 6 volts across it. So once again, we're going to use the charge equals CV equation. 1000 times 10 to the negative 3, which is of course the same as 1, which is rather large. Anyway, we'll stick with that, times 6. Yeah, so we're going to get 6 coulombs, a massive amount of charge, but there we go. Right, number 5, the charge on the 100 millifarad capacitor in the following circuit diagram is what we're asked to find here. So to do that, we're going to use the same old equation, Q equals CV. Plugging in 100 millifarads and multiply it by 20 volts in this case. We can see that that 20 volts is across that junction and that junction, which of course puts it directly across the 100 millifarad capacitor. So 20 volts is correct. We multiply 20 volts by 100 millifarads and we should get 2.0 coulombs. 2.0 coulombs across that. B, find the charge on the 10 millifarad and 47 millifarad capacitors respectively. Well, we need to find their combined capacitance first. So to do that, we use that ratio equation, 1 over 10 plus 1 over 47, all inverted. Doing that, you get 8.25 millifarads. So now we are in a position to calculate the voltage the charge on each, given the voltage of 20 volts again. So Q equals CV, where our C is this combined value, 8.25, and we're multiplying that by 10 to the negative 3 for the milli, and by 20 for the voltage. What does that give us? 1.65 times 10 to the negative 1 coulombs. Now, of course, that's the amount of charge on each of these two capacitors. So we just put each, perhaps. Okay, question 5, we're asked to find the energy stored by the 47 millifarad capacitor. So that's using the energy equation. The best one to use in this case involves charge and capacitance, since we have those already. So that's Q squared over C. Being careful to use the 1.65 times 10 to the negative 1 coulombs for the charge, the total charge we just found before, and dividing it by 47 millifarads, you should in theory get 2.9 times 10 to the negative 1. Oops. Joules, of course, for energy. Then, next, D, the PD across each capacitor. So we'll do the V across the 10 millifarad capacitor first, using Q over C. Again, making sure to use the total charge, 1.65, again, times 10 to the negative 1. Divide that by 10 millifarads, and you should get 16.5 volts. Leaving the remainder of the 20 volts across the 47 millifarad capacitor, so that would be 20 take away 16.5, or 3.5 volts. Okay, number 6, 200 millifarad capacitor is charged by connecting to a 20 volt DC supply. It is then connected positive to a 100 millifarad, which is uncharged. What is the PD across the combination? So, We can add the two capacitance values together to get our total capacitance value of 300. Why? Because they're in parallel, so it's very simple addition. And then use the voltage equation with Q upon C. Now we haven't got Q yet. Whoops, so how do we find Q? Q will be the 200 millifarads over the, multiplied by 20, of course. So we're just using CV, of course. So that's quite simple. 200 pi times 10 to the negative 3 times 20. And what does that give us? 4, exactly 4 coulombs. Now we have that. We can plug it into this equation over here. So it's going to be 4 divided by the value we just calculated, 300 times 10, to the negative 3. So the V, the PD equals, now of course this will be across both capacitors since they're in parallel, the same voltage exists across both, and that comes out to be 13.3 volts.